All right, welcome back to the ideal gas law section. We're going to end this section by doing a few more ideal gas law problems, now looking at how they relate to stoichiometry. So we're going to look at a few examples of what we can do and how we can use the ideal gas law when we're looking at a chemical reaction. Remember, like I said before, that when you're looking at a chemical reaction dealing with gases, it's important to look at what is the temperature and pressure of the room. And when analyzing a gas species in a chemical reaction, the ideal gas law can be used to convert liters of a gas into moles and vice versa when the conditions are not at STP. So you may recall back in previous topics that 1 mole of any gas at STP, which is standard temperature and pressure, occupied a space of 22.41 liters. And this was a very useful conversion. But the problem is, most of the time, the conditions are not at STP. And so when that's not the case, when the conditions are not STP, you can't use this. You have to use the ideal gas law. And that's what we're going to see. And just as a reminder, what's standard pressure and temperature? Okay, standard pressure is 1 atm. Standard temperature, be careful, it's 0 degrees Celsius. There's a difference between standard temperature and standard conditions. So just wanted to make sure I was clear on that. So STP are these conditions right here. Okay, so let's look at example 4. Consider the reaction of zinc with hydrochloric acid to produce zinc chloride and hydrogen gas. All right, so before we look at the problem itself with all the numbers, let's write out a chemical reaction for that. So a little bit of practice still with making sure you know how to write chemical equations. So zinc, okay, solid zinc, is reacting with hydrochloric acid, so HCl, aqueous. Now this is a single replacement reaction, so the zinc and the hydrogen are going to swap spots. So zinc is going to bond with chlorine. Now zinc's positive 2, chlorine's negative 1. You need to make sure you put the 2 there. Okay, so that's aqueous. And then, I'm kind of running out of some space here. Okay, hydrogen is the element now that's off by itself, but we don't write hydrogen, we have to write H2. Okay, and that's our gas. Making sure that it's balanced, it looks like we need 2 hydrogens on the reactant side, and that should balance everything out. So there's our balanced chemical equation. So now that we have that, how many grams of zinc, okay, so how many grams of zinc are needed to produce 20.52 milliliters of hydrogen gas? So the hydrogen gas over here, we want to produce 20.52 milliliters. And it's important to note, what are the conditions of the room? The conditions of the room are 825 torr and 25.50 degrees Celsius. Okay, so before we get into the math, let's take a step back and look at what's happening. This is a stoichiometry problem. This is going back to topic 9 when we first learned about stoichiometry. And remember, it's always the same 3 steps of stoichiometry. Once you've got your balanced equation, it's always take what you're given and convert it to moles. That's step 1. Use the mole ratio to convert to what you're solving for, so that's step 2. And then finally convert into the desired unit, which is step 3. So the stoichiometry is not changing. Here's what's changing. You're taking what you're given, and you need to somehow convert this information about hydrogen gas into moles. If the room was at STP, we could use that easy conversion we saw in the previous slide. We could use this to just simply convert into moles. The problem is it's not at STP. It's got these units over here that are not your STP units. So how do you get converted to moles? You use the ideal gas law equation. Okay, so I know, okay, for hydrogen, I know a volume, I know a pressure, and I know a temperature. It's not in the right units, we'll take care of that, but I know enough information to use the ideal gas law, right? So if the ideal gas law is PV equals nRT, okay, I'm trying to use all of this information about hydrogen gas to figure out the number of moles. That's the first step. So I'm trying to use the information to figure out N. So I'm going to rewrite this equation, okay, and I'm going to get it all set up to solve for N. So if I was solving for N, it's going to be my pressure and volume divided by RT. That's the ideal gas law rewritten so that way we're solving for N. And specifically, I'm going to put a little sub H2 so we remind ourselves what moles we're solving for. Okay, so let's plug in our information. So pressure. This pressure needs to be converted into atmospheres. So we're going to divide that by 760. So 825 divided by 760, I end up getting 1.09 atmospheres of pressure. So this is the pressure. 825 torr is the same thing as 1.09 atm. Next is my volume. My volume's in milliliters. I have to convert that into liters. So I'm going to divide by 1,000, or you can move the decimal 3 places to the left. So it would be 0.02052. Notice I keep all my digits, and that's now converted into liters. Divided by my gas constant R, that's the same, 0.08206 atm liter over mole Kelvin. There we go. And then my temperature. I got to convert 25.50 to Kelvin. So I'm going to add 273.15. This time I'm actually going to keep 2 decimal places because you can see I have 2 decimal places. So when I add that, 298.65 Kelvin. And so when I multiply all this through and divide, atmospheres will cancel, liters will cancel, Kelvin will cancel, and I'll be left in moles. So 1.09 times 0.02052 divided by my gas constant, and then divided by my temperature, 298.65 Kelvin. If I did that correctly, my number of moles of hydrogen is 9.13, and make sure you write everything, times 10 to the negative 4th moles. Okay, that's the same thing as 0.000913, in case your calculator gave you that. Okay, so it's not a lot of moles, it's very small, okay, and that's normal. So even though it looks different, that was the first step of stoichiometry. The first step of stoichiometry is take what you're given, convert to moles. And we did that. It looks different, but that step is now done. Everything else from this point forward is just a review. What's the second step of stoichiometry? Use your mole ratio. Okay, I want to get out of moles of hydrogen, and I want to get into moles of what I'm solving for, which is zinc. Okay, and there's a 1-to-1 ratio for moles of hydrogen to zinc. Okay, and make sure you show this step. Even though it's 1-to-1, you still need to show this step so you can show how moles of hydrogen are canceling out. Finally, last step, I don't want to know moles of zinc. I would like to know grams of zinc. All right, and looking at my periodic table, my molar mass of zinc is 65.38 grams per mole. So it was moles of zinc will cancel, and now that gives me grams. All right, final answer with correct number of sig figs. I need 3 sig figs, 0.0. Remember that 0 doesn't count. So 0.0597 grams of zinc. That's how much would be needed. And I kind of cut off my little decimal there. There we go. All right. So the only difference in this problem was that the conditions of the gas was not at STP, so we had to use the ideal gas law in order to convert to moles. After that, it was just regular stoichiometry. So we're going to do one more example. This is a very similar situation to what we just saw. I'm going to go kind of quick on this one, but feel free to pause the video first, work it out on your own, see how far you can get, then hit play to see all the work shown. Okay, so we already have the balanced chemical equation, so let's go ahead and start putting my information. Determine the mass of sodium azide needed for the airbag to produce 100 liters of nitrogen gas. All right, so 100.0 liters is what I want. The temperature is 85.0 degrees Celsius. Pressure is at 1.00 atm. All right, so this is all the information I'm given. I need to take this information about volume, temperature, and pressure, and I need to figure out the number of moles from that. So moles is PV divided by RT. Pressure, nicely, it's given to me already converted, 1.00 atm. Also, volume is already in liters. That's nice, so I don't have to convert that. Gas constant, 0.08206 atm liter over mole Kelvin. And then finally my temperature. That's the only one I do have to calculate. 85.0 plus 273.15, keeping one decimal place, 358.2 Kelvin. All right, calculating all of that. All right, I end up getting my number of moles is 2.29 times 10 to the negative fourth moles of nitrogen. Next is my mole ratio. I want to get out of moles of nitrogen into moles of sodium azide. And that is a 3 to 2 ratio. So 3 moles of nitrogen to 2 moles of sodium azide. Okay, finally, and I am running out of space, I apologize. I'm going to finish that down here. I want to know not moles of sodium azide, but I want to know grams. Okay, and so I need to figure out what that molar mass is. All right, molar mass of sodium azide is approximately 65.02 grams for every 1 mole. So final answer, 2.29 times 10 to the negative fourth times 2 times 65.02 and then divided by 3. I end up getting, and I'm going to write it in blue so it shows up a little bit better. Okay, I end up getting 0.00993 grams of sodium azide. You could have also written that in scientific notation as well, which would have been 9.93 times 10 to the negative third. Okay, either one is fine. All right, but that would be the amount of sodium azide that would be needed in order to produce that much nitrogen gas. All right, well, that wraps up the ideal gas law. We'll see you in section 4 where we talk about the rest of the gas laws.